Transformation surface. So this example shows a rectangular surface and then producing this tapered surface. So the function is we have the purple surface, which is, well, this is the destination surface. This is tapered. And so this adds shape and complexity at the destination. The purple is a rectangle, which is just a Cartesian coordinate system, if you please. It's a flat surface. And then lastly, we have, in this case, the upper part of a wing, an airfoil. So the mapping system is from the rectangular surface, the flat rectangular surface, to the flat tapered surface. And that measures the height of the rectangular airfoil here, and then calculates its new position relative to the tapered surface. So the rectangular surface, we have the U going front to the back and V going root to the tip. Likewise, this surface is set up the same. So V is root to the tip, U is leading edge to the trailing edge. So a surface is an infinite number of points. So by deforming the destination reference surface, we can easily create a new wing in a new position. So let's look at how this thing maps. So once again, a surface is an infinite number of points. We're just going to look at one sample point. We're going to create a point on the rectangular reference surface, giving it a U value of 0.25, V value of 0.75. So that locates it, in this case, literally the equivalent to a Cartesian coordinate system. Let's put the equivalent point on the tapered surface. So we're going to use parameter spacing, U of 0.25 and V of 0.75. So now we have 2 points on each of the individual reference surfaces, the starting reference and the ending reference. We'll create a normal line, which represents a normal vector. So create a line, and then we'll test to see how far away the surface is over that point. So we'll do a measure, capture the measure, Control C. Then we go to the destination surface or reference surface, where we have already calculated where the point is. Then we're going to create a vector normal to the reference surface at that point. So this is no longer in the Z direction. This is some twist relative to the twisted destination reference surface. We paste in the measured distance up that vector. So we've created a vector, we've offset a point, and then we measure that point to the surface, and we find that it's quite close, or essentially on that surface. So this is the simple method that we use to create a transformation surface by using a simple reference surface, and then two systems, in this case rolled surfaces, that maps the original simple surface onto a more complicated destination surface.